request Ramrao sir to take over the session.
Yeah. Good morning to all. Thank you, ma'am. So thank you, and it's a pleasure for me to provide a discussion with you all. So currently, like I'm based at Canada. So my base location is Montreal. So currently I'm working for Airbus Canada. Early it was Bombardier. So recently 1 year back, the Airbus took over Bombardier. Took over the Bombardier. So currently, like I'm a system engineer for the electric systems and avionic systems group. So usually we will participate in the discussion, then technical snacks and daily technical discussions with the pilot and the Transport Canada. So for the with respect to the design aspects. So yeah, so today I'm planning to provide an overview of the advanced avionics and as well as the fly-by-wire flight control systems. Then what are the regulatory complaints? So we are going to perform with respect to the systems design. Then once that is done, then I will move over to a brief introduction for electrical systems actually. Then as recommended by Prasanna Kumar, so he told me to give just a brief introduction of flight data recorder. That is what we known as black box. So then I will end up with the conclusion. So this is my today's agenda. So are you able to see my presentation?
Yes, sir. Yes, sir. Yes, sir. Continue. Continue.
Okay. What about am I audible?
Audible also. Yeah, audible.
Okay. Thank you, sir. Okay. So just I would like to introduce about aerospace engineering or on the flight. When I was supporting for Boeing aircraft in USA, whenever I used to enter the facility, I used to see the display board. Then there was a curious from my side. Okay, what exactly they would have been written on the display? Then I went and I saw these wordings. So I believe this will provide a self-explanatory with regards to the flight introduction. So once again, I would like to read. So from prehistoric times, humans have watched the flight of birds and longed to imitate them, but lacked the power to do so. Logic dictated that if the small muscles of birds can lift them into the air and sustain them, then the larger muscles of humans should be able to duplicate the feat. No one knew about the intricate mesh of muscles, sinew, heart, breathing system, and devices not unlike wing flaps, variable camber, and spoilers of the modern airplane that enabled a bird to fly. Thousands of years and countless lives were lost in the attempts to fly like birds. So as we know that, so we are all engineers. So we need to develop a system in order to imitate the bird. It's very difficult for us to design a actual system. So as we know that we will face a lot of challenges. So we have to bring down the real scenario, real requirements to a in form of software hardware. So just to bring a small piece of requirement, it will take a lot of challenges, and we have to put on the paper to bring as a life. So this what I say, as we know that so lot of logic will be involved to bring a very huge complex system. As we know that aircraft is a complex system, and it has a subsystems. So as we know that, So in the design stage and in the operating process, to ensure the continued airworthiness of the aircraft, so we have to break the aircraft. If you take aircraft as a system, in the aircraft we have so many subsystems. So for example, so engine is a subsystem of the aircraft, avionics, flight controls, landing gear, electrical system, hydraulics, and so on. So all together, all the subsystems has to integrate, and finally it has to play the role of a aircraft. So it's very hard. So being like usually whenever we used to do a system integration level testing, and we will have a discussion with the other OEM vendors, like they provide the avionics systems and softwares, and engine is integrated to the aircraft. So usually during the system integration, we'll face a lot of issues. So we especially with respect to the communication, we need to provide a proper communication. We have to establish the proper communication. So these a lot of challenges will be occurring during system integration. So once everything is fine, then from there we'll go for the flight certification. So we have to get the flight certification from Transport of Canada. So if the aircraft is built in Canada, so we have to approach Transport of Canada. If the aircraft is built in US, so we have to approach FAA regulatories. So then I will move to the next slides. So as I mentioned, so avionics is one of the subsystem of the aircraft. So as we know that avionics, currently, like we are talking about advanced avionics systems can automatically perform many tasks that pilots and navigators previously did by hand. Have you go back to 1950s, 1940s? We had a traditional way of instruments. So where the pilot has to put 100% 100% effort for the navigation and for the flight phases. But nowadays, with the extent of electronics and computer science, so we have advanced so much that we are able to achieve the autopilot system in the aircraft. So where we have a proper waypoint and plans, then the flight itself will take over the automatic configuration, and it will provide the less burden to the autopilot pilots. So in order to achieve the accident prone errors, so that is the motivation, and that is the behind of avionics subsystems. So as we know that avionics are the electrical systems used on aircraft, and not only for the aircrafts, for the artificial satellites and spacecraft. So currently, like I'm working on a project. So where, as we know that, so during crash, whenever the aircrafts occur a crash, so we need. It's very difficult for us to find out the wreckage of the flight actually. So it may take several months or several months. So we'll have a flight black box, but it will the life of the flight box will be around maximum 30 days. So within 30 days we need to find out the aircraft, otherwise we may lose all the data. So so why I'm suppose when the aircraft is in the distress condition, then our intelligence and system will sense and will collect all the critical parameters from the subsystems, and eventually it will transfer the critical parameters to ground station via satellite. So I believe like nowadays we are planning to share the data through the iridium satellites. So this might be the next challenges for us. So whether flying a conventional aircraft features a global positioning system, GPS navigation, receive, or a new aircraft with the latest integrated glass cockpit advanced avionics systems. As you see, like right side, the right side. One second. So the right side. So I have just have shown the cockpit. So cockpit which has taken from the internet. So this cockpit is from 787 Dreamliner. Have you? So we have couple of we have MFD multifunction display and DCMU and head of displays actually. So this has a complex avionics environment. So in order to achieve the complexity, so all these subsystem will integrate with core avionics platform. So a sort of cockpit information system provides pilot with data about position, then plan route, engine health and performance, as surrounding weather, traffic and terrain. So it's these are very important data to achieve a successful flight. So usually from the pilot, he will get all the information related to ongoing weather forecast. So this is very helpful for them to continue the aircraft. So I will move to the next slide. So this right side I have I have depicted two pictures, so where you can see the placement of the the boxes. So in terms of aerospace engineering, we will call these units as a LRU. LRU means line replaceable unit. So the function of the main fundamental of LRU is, if in case if this LRU is not non-functional, then we can take out the LRU, and then we can fly without any impact to the aircraft systems. That is the design of the LRU, and we'll have redundancy. So if this particular LRU goes off, then we'll have other LRU which will perform the function, which will perform the functionality of that particular system. So as I mentioned, so we have the right now we have the capability of autopilot. So the autopilot means because of the advanced avionics, so we are able to achieve that autopilot concept in the aircraft. So not only in the aircraft, I do believe like right now we are seeing the autonomous driving system. So some of the things have been derived from the aerospace industry to the automotive industries. So the main heart of the avionics is flight management system, FMS. So HARNAV, or these FMS is the heart of the avionics. So FMS so is integrated in the cockpit. So we'll have two FMS. So to FMS, so FMS will get the data from all the subsystems of the aircraft. So all the so we will have couple of datas like Ring 717, Ring 429, can data. So all these data will will be will be passed through the avionics system. That is what we call DCU. So distributed computing unit. So it will collect all the data from the subsystems of the aircraft, and it will process, and it will finally pass to the FMS. So where usually the in the cockpit, I believe like we have seen in the previous slide, so all the data will be shown as a graphical form, or in the real image form, so that it is very helpful for the pilot to understand the current scenario or current scenario condition of the aircraft to in order to achieve successful flight. So as we see that advanced avionics perform many functions and replaces the navigator and pilot in most procedures. So I do believe like because of the introductions of the advanced avionics. So pilots, they can have the capacity to fly the aircraft very easily and smoothly without any prone to error. So similarly, information systems now available in the cockpit provide many options for the obtaining data relevant to the flight. As I mentioned, suppose assume like we have suppose if the waypoint is fixed, waypoint is fixed. If there is any issue or if there is any flaws during the flight phase, I do believe like so depending on the condition, so they can change the flight plans based on the avionics output. So coming to the advanced avionics systems, so advanced avionics systems present three important learning challenges. So because I believe like in the last slide we have seen the cockpit. So in the cockpit we have so many multifunction displays, so many systems. So it's very hard for us to digest, okay, what exactly the one MFD does. And so it's very hard for us to understand the functionality of the system. So it will take, so assume that the pilot, they have to drive the flight in such a manner, they should be aware of the all the subsystems. So okay, so that is the challenge for them. So they anyhow we will design the systems, so we will install the systems in the aircraft, but at the same time, so they need to educate themselves, okay, how each systems perform at suitable conditions and suitable modality. So that this is the challenge for them, how to operate the advanced avionic systems. And each aircraft has its own own instruments, but relatively like okay, the underlying principles are same, but the way of handlings will be different. So each aircrafts will have their own perspective and own methodology. So these are the some of the challenges for the crews actually. So, as I shown in the slides, the upper pictures. Upper picture depict the LRU. So this is the bay of the aircraft. I do believe all the avionics LRU means boxes will be seated in the mid avionics bay. If you take the aircraft, we have mid avionics bay, aft bay, and forward bay. So all the units or line replaceable units will be placed in mid avionics bay or aft avionics bay. So yeah, I will move to the next slide. So as I mentioned, so we have so as we seen in the cockpit, we have flight instruments. So these flight instruments or it's a digital flight instruments. So as we know that we have analog flight instruments. So apart how we design the cockpit cockpit, so we'll have all the digital flight instrument. Apart from that, suppose in case if we lose these flight instrument, then have a redundancy, means you will have a analog flight instrument also. So the pilot has to know how to read the analog signals. So this is the way how we design. Suppose in case if we lose all these channels, okay, the backup will be the analog instruments. So coming to the primary flight display, PFD. So PFD, it's nothing but a computer. So advanced computer, it's electronic flight instrument systems available with advanced avionics. So the right side is one of the example of the PFD. It is seated in the cockpit. So we'll have like a totally like five PFD or MFDs. So that's depending on the aircraft configuration. So the mid-size aircraft will have 5 PFDs, whereas the business aircraft will have three PFD depending on the configuration. So all these are collectively wired, and it's connected to the subsystems of the aircraft. And finally, take for example, we have actuators, and actuators will be actuators. then that is directly coupled to the sensors and controllers. So then we can fetch the data of the controllers and sensors, and we can see those data on the primary flight display. And at the same time, the pilots can control the sensors and sensors through the PFDs. So as we see the rightmost display, that is the primary flight instruments. As so if you see properly, like we have we have like the conventional we have conventional GPS, then the left side the altitude and altitude, those things will be depicted on the primary flight instruments. So I will move to the next slides. So as we know that the primary flight instrument systems, the primary flight instruments that appears on a PFD are driven by instrument sensor systems that are more sophisticated than conventional instrument systems. The attitude of the aircraft may be measured using microelectronic sensors that are more sensitive and traditional gyroscopic instruments. So these sensors measure pitch, roll, and yaw movements away from a known reference attitude. Aircraft heading may be determined using a magnetic direction sensing device such as a magnetometer or a magnetic flux value. So if you see the left picture, where we have a computer, it's I can call as a linear LRU. So it is connected to all the sensing elements and sensing element, and as well as the commanding elements. Then so it will process the signal. Again, it will perform proper controlling mechanism on the hydraulics or rudder or elevator, as we have seen on this picture. So what I meant to say is we can capture, we can see all the signals so from each sensing element or a sensing element, which will be controlled by the dedicated LRUs or computer which is fitted on the aircraft. So the attitude and heading systems are typically bundled together as an attitude heading reference system, HRS. So which contains not only the sensors used to measure the altitude and heading, but also a computer that accepts and performs the calculations. So I will move to the next slide. So in this figure, have shown these are all the down element, the down unit. This is called the ADSP probe, we'll say. So and the main function of the ADSP probe is, so it will sense the altitude and outer side temperature. And these sensors are very sophisticated sensors. So what is and as we see that early, like we used to have a traditional air data system, so where we can see like a lot of wirings and a lot of units have been integrated. So now coming to the the advanced smart probe, where we have less wires and less systems. So I believe like ultimately we can reduce the weight of these wirings and units actually, and that will have a way efficient that will leads to the efficient. So information on the altitude and airspeed is provided by the sensors, so that measures static and ramp air pressure. And so we have, I believe like the air data probe sensors, we will have like at least four air data probe sensors have been installed on the aircraft. So because in order to meet the redundancy principle, suppose if one ADSP probes and will be non-functional, then we'll have other ADSP to take over the functionality. So that is the principle of the redundancy systems. So as we so these sensors these sensors will have like will collect the the will collect the data, and those data will be transferred to the avionics main box, and again we will have the avionics main box have a process. They will perform the processing and calculation, and again the signals will be fed to the different subsystems through the avionics box. So I will move to the next. As we've seen the topmost right hand side, so where we have the ADSP probes, two ADSP probes, and one the middle one is the ice detection system. So as we know that the aircraft will fly around the altitude of 40,000 altitude, we do believe like the atmospheric temperature will be around like minus 50 degrees C, above minus 50 degrees C. So in order to have a proper condition, I do believe these ice detection system for every 250 millisecond it will sense, okay, if any ice has been built up on the aircraft structure. So if it sense, then within a fraction of a second all the ice will be melted actually. So that is the functionality of ice detection system, which is depicted in the center of the picture. On the top and the bottom, that is those are ADSP probes. So air data sensors probes, so which will sense the speed and the atmospheric temperature. So increase in air traffic, operating cost, and performance demands have made precision air data measurements necessary for safety, economy, and maximum performance. So I believe suppose take for example, if the aircraft is in like in Canada or US, so especially during winter season, where I believe temperature will be like around minus 30, minus 40 degrees C. So in order to perform the flight operation, so we do believe we need these systems. So for further process, otherwise it will be very difficult in order to move forward. The right pictures is the total air temperature TAT sensor. This is one of the sensing element is fitted on the aircraft. The TAT sensors are among the leading precision sensors available. So designed for all weather use with temperature ranging from minus 94 Fahrenheit to 662 Fahrenheit. So in terms of degrees, minus 72, 350 degrees Celsius. So these sensors are highly sophisticated. It's a very need for the efficient flight actually. So I will move to the next slide. And so I believe I have concluded with the avionics. So then I will move to the next subsystem fly-by-wire system. So which is electrical flight control. So as you see the left hand side, so early the conventional aircraft used to use and wires in order for the proper for navigation purpose actually, okay, for the flight path. But nowadays, because of advanced technologies, so we have fly-by-wire systems that is called electrical, like in terms of electrical flight control, we can control the flight through the electrical technology. So what are the problems we have faced during the traditional way? Like early we used to have the mechanical and early we used to have the flight controls, which is through the hydromechanical. So I believe like we had a lot of issues. So those are like control relatively those are heavy and require careful routing of flights. Control cables to the aircraft by systems of pulleys, cranks, tensions, cables, and hydraulics. So if you see the picture, I do believe they like it's very hard. It's very hard. All these harness would have been rusted or gone. So we don't know. As we know that aircraft is a subsystem, so we'll have multiple harness. So it's very hard for us to detect, okay, which particular harness has gone bad. So in order to rediculate all those things, I believe we have like the advanced electrical flight control, which will take over all these issues. Both the systems often require redundant backup deal with the failure, which increase the weight. Both have limited ability to compensate for changing aerodynamic conditions. So this is one of the advantage of having electrical flight control on the aircraft. So a fly-by-wire system is a computer-based flight control system that replaces the mechanical link between the pilot's cockpit controls and the moving surfaces by much lighter electrical wires. Also replaces the conventional manual flight controls of an aircraft with an electronic interface. So yeah, I will move to the next slide. As we see, okay, what are the advantages of the flight control? Means fly by or fly electrical flight control. So flight envelope protections, we have very good flight envelope protection. Then the stability and handling qualities are very good. Then especially the weight reduction. So that is one of the major factor, and the maintenance reduction, as I mentioned. So we will have lot of wires. We don't know which wire has gone bad. It's very difficult for us to investigate. Okay, so which wire has broken. So it will take long time in terms of maintenance. So that will reduce the maintenance reduction cost. So and also fuel efficiency. If the main thing is if the aircraft weight. Suppose if you will reduce the burden of the aircraft, I believe like will ultimately will achieve the fuel efficiency. Then we'll have higher stability and some of the others advantages. So then what are the effects? So because of this, what are the effects? So like the effects are increased weight of the aircraft system, increased complexity. So obviously, like if the aircraft has more complex, it's very hard for us to understand the systems. So then less survivability, then fuel inefficiency. So these are all some of the effects which the traditional mechanical hydromechanical flight control system has. So so that uh, the diagram shows, okay, we have the cockpit where pilot the pilot controls the input. Those signals will be directly directly fed to the actual actuator control electronics. We have dedicated so control electronics unit which it will sense the signals, and then again it will process, and again it will take the action on particular control surfaces on the aircraft. For example, we have spoilers, ailerons, flap ailerons. So it will take the control all of this, and so it will guide the flight in a proper direction. So I believe that ultimately we can call as a autopilot. Yeah, then I will move to the next slides. So this is just I have given just brief again the brief how the flight control system, what is the flight control system layout in exactly on the aircraft. If you see the right hand side a diagram where we have the subsystems. These are the flight control main control subsystems: aileron, spoilers, flaps, and elevators. These are the main subsystems which drive the proper path or directions for aircraft actually. So all these subsystems will be controlled by the fly by wire through electrical means of communication. So the first electrical flight control system, so we can say fly-by-wire system, so was a civil aircraft was designed by Aerospatial and installed on the Concorde. So this was the first aircraft which was installed by the flight control system. The first generation of electrical flight control system with the digital technology appeared on several civil aircraft at the start of 1980s. So I do believe like after 1980s, so there is a tremendous growth and improvement towards flight control systems, and later on the flight control system have been evolved in so many versions. Right now we have like quite matured enough flight control systems on all of the fleet of the aircrafts. So as I mentioned, like the primary flight control, so the ailerons, steering spoilers for roll control, elevators for the pitch control, the rudder for the yaw control, secondary flight controls, inboard and outboard flaps. So these are all the main primary flight controls. So the then okay, then I will move to the next slide. So then how do we design the systems as I mentioned, like on failure and dependability. So so then suppose if the system has so systems been failure, then what is our backup? So then I believe like that we'll have some dependability also. The flight control systems are built to very stringent dependability requirements, both in terms of safety and availability. So we will have like dedicated left channel and right channel systems. Suppose if in case like I do believe like each system will have at least up to eight level of redundancy. If left in the left channel again we will have two sub channels. In the right channel again we'll have two other sub channels. You mean to say at least two like no four redundancy system redundancy concept will have. So as I mentioned, like so again in terms of the criticality level of the component of the software and hardware will classify okay whether this system belongs to DAL A, DAL B, DAL C, DAL D means a design assurance level. Whether if the system if the subsystem comes under DAL A, then that will be called as a catastrophic. Suppose if there is a failure, I do believe so, then there is a major loss of the aircraft. So during the design and development, we have to follow very stringent requirements. I do believe like we will get the all the we will follow the stringent requirements through the regulatory requirements. So we have some set of regulatory requirements from the FAA, Federal Aerospace Aviation. So that is from US, and Transport of Canada from Canada. Then again in Eurocar from ESA from Europe. So those regulatory requirements will set and will mandate okay when you are planning to develop these systems, we no matter what we have to follow the stringent process. And when we develop these subsystems, so we need to apply for the type certification. Then we need to show the artifacts okay we have taken care of all these, and these are the proof in order to say that in order to prove that this system has the capability of level A in terms of software or hardware. So when it comes to software, so we have we will follow Devo 170 BRC for the in order to assure the design assurance level, and for the hardware component we'll follow Devo 254 guidelines. So as I mentioned, like the system's failure due to physical. So no matter what, we need to follow these the regulatory requirements, and otherwise advisory circulars that requires demonstrating that any combination of failures with catastrophic consequences is extremely improbable. Typically addresses failure. Extremely improbable is translated in qualitative requirements and to probability per flight hours. So you're when we are talking about complex system, especially in the aerospace industry, so we need to provide artifacts. Okay, we have taken care these requirement, and we the high top from the top level requirement till up to the coding or up to the end, we need to provide the traceability. So how we have achieved, so those things will provide the artifacts and so proof of mechanism to the regulatory agency in order to satisfy the criticality of the system. So I will move to the next slide. So as I mentioned, yeah, the redundancy again. So currently, like I'm working on the electrical systems. So in our system, we have minimum like around six redundancies. So I want to say, suppose if one system one system has malfunction, then I will have backup. So at least we'll have at least four backup. So that is the level of redundancy I will have in the subsystems of aircraft. So especially when I'm talking about the redundancy for the flight control, the redundancy accept is handled at system level. As I mentioned again, the collectively like we'll have the system level redundancies. So again, the failure detection, when it comes to the failure detection, so typically computer runs itself self-test and test its peripheral during the power up of the aircraft, and therefore at least once a day. Okay, we are like okay, we take for example, we have rat a ram air turbine for the electrical system where it generate 12 kVA 12 kVA during the emergency. So but I do believe like in from 1970 till up to now, yeah, we never used rat actually. You mean to say rat, that is for the emergency power supply. So suppose if you're not using means, then we the system engineer, we need to design in such a way that no matter what, so during each power up or during each power up, we need to perform the self built-in test. So whenever there is a initial power, yes, so perform the power built-in test on that particular system. We to say like for within 250 millisecond, the contactor has to open and close and check whether that particular hand system is functionally good. So like this we will what we will provide the requirement for the end system in order to ensure that there should be no failure. So then, as I mentioned, the component redundancies. So so as we know that we have some backups. So in terms of power supplies, so no matter what we need, so DC power, DC and DC power. So basically, like the end subsystem will be getting the power from the AC source or DC source. Suppose if these sources are not available, then what will be the backup? I believe like the battery, otherwise the RAT. So we'll have at least a backup of redundancy. So in terms of power. So yeah, I will move to the next slide. So then again, while designing, we have to consider the error avoidance. So aviation guidelines are applied with the highest level of development assurance level, as I mentioned, the DAL level A, so which is catastrophic. So we will have some set of rules or checklist. So no matter what, we need to follow those checklists while designing the system. So if it's a level A, it's a high level component. So then if there is a system failure, as I mentioned, there is a huge loss for the aircraft. You want to say loss of death actually. So loss of death. So in order to achieve the level A competent, no, so we need to follow DO178C for the software component and DO54 for hardware component. And this is with respect to the subsystems. So when assume like the aircraft, we will consider aircraft has itself a system, then again we will follow ARP 475A for the safety in terms of safety. So that is the standards for the entire aircraft. So usually the manufacturers, they will follow 475, and whereas level DO170B, DO178C and DO254 will followed by the OEM vendor or suppliers. So to the design and manufacturers. So these errors are addressed by FAR, so again the regulatory agency that mandates to follow a stringent development process based on the following guidelines. As I earlier mentioned, okay, ARP 475, so that is for the FAA for the aircraft system development. As we consider entire aircraft as a system development, so we will follow as per ARP 475 4 guidelines. Then DO170 for the software development and DO254 for the hardware development. So then as we so these are all the regulatory requirement, no matter what we need to follow in order to achieve the certification level and priorities. So there is no clear requirement that a design must be design fault tolerant, except if the applicant wishes to reduce its development assurance effort. So no matter what, so we have to provide the proof, so stating that okay, so suppose if our system is a complex system, so we have taken care all of the regulatory requirements. Yeah, I will move to the next slide. So yeah, so there I have so I have concluded the flight control principles and mechanism. Now I'm moving to the electrical system overview. So as we see that, so this picture, this is from the Boeing 787 aircraft, Dreamliner aircraft. As we see that, so the Boeing 787 has 6 generators. So each generator has the capacity of 235 kVA. So if you see the generators are integrated into coupled with left and right engine. So left and right engine. So overall, I do believe like the flight we will have 1 megawatt power will be generated during the flight phase actually. So as we see that electrical loads, so the right hand side is forward electrical load where power receptacles will be there. So usually like suppose if you in order to power the aircraft, so we have different modes of operations. So we can power the aircraft through batteries. We have 2 batteries, lithium ion batteries. So you can in emergency we will power the aircraft. Otherwise, usually like we will power the aircraft through the ground card. So ground card which has 235 yeah, 235 volt AC power. So those are the power receptacles. Directly we can connect to the aircraft and we can power the aircraft. So I believe like we have seen those ground card in the airport terminals. Suppose if you don't have air card, then then through the batteries, and then we have common motor starter controllers where it will initiate where we can where we can crank the engines, and once the engines are cranked, I do believe like we'll get the power to the entire aircraft through left and right generator. So we'll have at least 235 volt AC from the left and right, 235 volt AC, which so that will power. And I do believe like we have so the AC power, then some subsystems we need DC powers also. Then we have common distribution centers where the AC power is fed to the distribution channels. And again we have dedicated solid state power controllers, so that will take the configuration modality in terms of automatic configuration or in terms of manual configuration. So depending on the load budget of the aircraft, the solid state power controllers will decide okay whether the subsystems need the power or not. So take for example during the takeoff, I do believe like only minimal load means only the critical systems will have the power. So otherwise all non-critical components we won't have power. Once the the flight comes to the cruise mode, then we'll have power to all the systems, so no matter what. So those configurations will be taken care by the solid state power controllers. So where it will decide okay whether the aircraft is in which mode, whether in road mode or flight mode or decide mode. So depending on that mode, so we have dedicated the bus power controllers. So those are the units which is fitted on the left and right side, where you can see the 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 yellow boxes. Those boxes are the line replaceable units. So each each left channel and right channel will have dedicated the bus power control unit. So that will control the all the buses and as well as the loading mechanism in the aircraft. And apart from that, we have dedicated generator control unit on for each engine. So it will control the generator. So it will control the generator, and it will take further actions on it will control the generators actually. So and we have the APU auxiliary power unit. So we have dedicated GCU to control the APUs. This is the overall electrical system overview. And I will move to the next slide. So taken as a reference from the 787 electrical system architecture. So as we see the traditional aeroplane, as we see that 787 electrical system architecture, the traditional airplane, one generator on each of the two main engines and one generator on auxiliary power unit. So power feeders run from generator to the front electrical equipment bay. where you take the 787 Dreamliner. So we have 2 generators on each engine and 2 generators on the auxiliary power unit. So means totally we have six generators on the aircraft. So power feeders run from generator to the left electrical equipment bay. So we have a dedicated power panels. So I believe like totally like around 8 power panels will be installed in the mid and aft base. So in order to control, in order to take the control. So then we have like at least 17 small electrical substations provide power to the local loads. As I mentioned, we'll have CDCs, distribution centers, so cabinet distribution centers. So at least we'll have 17 CDCs on the each aircraft. So what are the benefits? I believe the total length of heavy gauge power feeders is less. So all these in order to achieve the weightage of the aircraft. So that is the main reason, main goal. If you reduce the aircraft weight, I do believe like we'll have power consumption and efficiency. That is the main goal towards all this. So yeah. So just in order to show okay how exactly the we have what do you mean to say, these are all the pictures from the multifunction display MFDs in the cockpit. Okay, how the pictorial representation will be look like. So just I have shown these two pictures. The left picture is the electrical synoptic display. Okay, so basically like as I'm a system engineer, suppose if we have an issue on the aircraft, so how I will proceed. So initially I will get the information from the technicians. Okay, so then okay, what do we have, and so what all the configuration, or whether the aircraft is in battery mode or electrical mode, or whether it's in the whether it's in the ground station. So first we'll take the information, then the first line of contact is the display, means the electric means the display. We need to get the data from the display. What I mean to say is OMS data. We'll say OMS, onboard maintenance system data. So collectively, as I stated in the initial, the advanced avionics, the avionics subsystems will collect all the information from each subsystems. So I believe like every 250 milliseconds we'll have the data on the display. So if we populate on that particular subsystem, so we have designated ATA chapters. So for each subsystem we have ATA. So for electrical system 24 and avionics 25, like that it has been designated. So if you populate on the particular OMS page, so this is the page number of pages. So we can see the we we can narrow down okay what is the issue on the each subsystem. So it will provide the detailed information. As I mentioned, we have like ring 429, ring 717, all these are the protocols parameters. So we'll have labeling structures. So we'll come to know okay what is happening with the real subsystems. Just in order to show okay how exactly look like on the electrical synaptic display. So as we see, we have power also. As by saying this, we can say okay, right now we have the left channel, the only we have the aircraft is powered through left generators and the EP generators, where we can see the green solid lights path actually. Okay, so this is the indication. Okay, the aircraft is right now powered by the generators, by left generator or right generators. So this is the indication. And coming to the right picture, so these are the picture for the CB means circuit breakers. So we have thermal circuit breakers, and also the electronic circuit breakers. So in order to for the protection, suppose assume so if we have so some transitions, then we need to provide protections for each subsystem. So then if we populate on these CB pages, so we can sense okay what is happening on each subsystems actually. So this is the status of each CB, just in order to feel how the displays will be look like on the in the cockpit. So yeah, I will move to the next slide. this is the single line architecture from Google, taken from the internet. So this is not dedicated for any any configuration, means aircraft configuration, just in order to see how the electrical signal, how the architecture looks like on the electrical in with respect to electrical system. So as we see the single line diagram, we have like the left channel, the right channel, and the center channel. How that's the way we will divide in. We will divide in the aircraft. Okay, the left channels is the left generators, right channel is the right generator. If you say left generator means that's the left engine, right generators means the right engine. So the generators are coupled, integrated with the engines. So we'll have the engines from GE or Rolls-Royce, otherwise Pratt and Whitney. So depending on the configuration. So once assume like once we have again it has the broadly it has been classified into three stages. One is AC power stages, then again again we will have essential buses, and again DC power. So as I mentioned, like in the aircraft, the load the subsystems with the load, if I say loads means, okay, so the subsystems will have AC or DC loads actually. Okay, then we need to provide a proper path for the subsystems. So again, as I said, like we will follow the redundancy system design. So when you talk about the redundancy system design, so, so that's why, like if you see, we have totally 1, 2, 3, 4, 6 generators. Assume like if the left channel is non-functional, then the APU channel and the right channel will take over. So assume left generator at the left, the APU channel is non-functional, then the right channel will take over. So this is the level of redundancy we can see in the aircraft. So this is with respect to electrical. Same manners we have redundancy. We have provided the redundancy for all subsystems. For the engines also, we have two engines. If one engine is non-functional, we have the another engine. So landing gear system, so hydraulic systems, also all the subsystems will follow the redundancy. So we'll have a backup plan. So has the AC, so AC is generated, so then the AC will be, so will convert to the DC with respect so through the TRUs, transfer rectifier unit. So then we'll have the AC bus, then DC bus, and again we have the essential bus. So the essential buses are for so for the critical unit. So even though in case of failures, no matter what, the essential system should have always power. So that's how they have been classified in terms of electrical power. So yeah, then I will move to the next slide. Okay. Yeah, yeah, yesterday, like just Prasanna sir told me, okay, Ram, it is better to include the black box also in your presentation. So as we know that black box, everybody knows, okay, black box. So initially the first thought will be, okay, black box will look like a black box. So eventually, no, the black box look like orange actually. So if you see black box, which are actually orange, are a group of data collection devices mounted in the tail of an aircraft. So if you if you see the right side picture down, so where the black box will be fitted in the in the tail of an aircraft. So so all collectively, like we have two boxes. One is flight data, means of flight data FDA, flight data recorder. Another is the voice recorder CVR. So these two boxes collectively called as a black box. So black box, which looks like orange in color. Why we have given the orange? As we know that So it's easily we can easily locate the box. So that's the reason we have given the orange color in order to find out properly. So the David Warren, an Australian aviation scientist, proposed a flight recording device, and by 1950 had produced the prototype ARL. So that is flight memory unit. So that the Dr. David he invented the black box. Okay, we need one mechanism where we need to capture all the ongoing flight parameters. Okay, suppose in case of an accident, okay, so we need to understand what happened in the aircraft with regards to the system. Okay, whether there is an issue with the design, or if there is any malfunction, or if there is a like a human error. Okay, in order to mitigate those, okay, it's better we'll have a recorder. So as we know that avionics so will sense all the signals from the subsystems, and again have like in the cockpit it will be depicted in terms of pictures, or relatively with regards to the proper notification on the MFTs. Okay, so as we know that so with the with the modern technologies devices which has been fitted in the aircraft, I do believe like at least like each aircraft during one flight phase means during flight hours, at least it will generate 1 terabyte of data. So 1 terabyte of data is a huge amount of data. So, but we won't record all those data, 1 terabyte of data in the flight recorder. So as I mentioned, we have regulatory agency. So they will say, okay, so no matter what, no need to record all the data, but it's very important to record the critical parameters. So as per the standards, I do believe like we have around 320 parameters. So the maximum parameters from the engines, I do believe engines. So like airspeed, then temperature, then flap, all those things, all those critical parameters will be stored in the black box. So I believe like roughly like we will have around nearly around 400 MB of 400 MB of data. So 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 um, so the computer, so have you seen so the flight data acquisition unit. So we generally will say DAC, data acquisition center, DAC. So DAC will collect all the what parameters from the subsystems of the aircraft. So we have dedicated left channel and right channel. The DAC then the DAC will send the data, share the data to the FDA, so flight data recorder. So flight data recorder. So in that manner, so as per the regulatory agency, so we need to record the flight data recorder should have at least 25 hours of flight data. So that is with respect to the flight data recorder, and we have cockpit voice recorder CVR. So in the CVR, so we need to record at least 2 hours of voice, to 2 hours of voice. So we have totally four channels in the aircraft. So we need to record at least 2 channels for at least for maximum 2 hours. So that is the regulatory requirement. So what is the main intention of recording these parameters? Suppose assume like if there is if the aircraft crashes, so then I do believe like the flight the regulatory agency and the government body will search for the flight data recorders, and again they will go for analysis, what went wrong. So for that purpose, yes, so we need to record at least 25 hours of data. So at least we can see, like, suppose if you have an intermittent problem, or really we do have any like subsystems problem. So this is one of the requirements for the regulatory agencies. as we see like the generations of the data recorders. As I said, like 1958 was the FDR was invented, and that time like we had a first generations of foil recorders. The data usually used to record in the foil. We had another second set of generations. It was the usual that was the flight data recorder was recorded through the tape recorders. Then again the third generation, now we are in the third generation, so that is solid state recorders. So as you see like the left the uh, the left unit is the cockpit voice recorder. As I say, the the components of the black box consist of one CVR, cockpit recorder, another flight data recorder. So each aircraft will have, each aircraft should have these two unit, which is fitted on in the tail. So the FDR will record all the critical parameters, whereas cockpit recorder will record the conversation of the flight crew conversation at least for 2 hours. So the right side picture indicate so the the down level of the how the solid state recorder, if we take off the unit, so how it looks like. So we have aircraft interface board. As I said, like all the datas will be will be collected through this aircraft interface board through the avionics unit. Then if you see we have high temperature insulation. So especially these FDR, these units will be engineered in such a fashion that so they will have robust in nature. Assume like it has to withstand the high temperature, high pressure, and high gravity. So you should not break. So that is the main intention. So they will have a robust inbuilt system, especially for the FDRs. We see this is the memory interface cable, like stacked memory boards where the data will be get stored actually. As like modern data recorder, so it is the currently the recorders made of strong materials such as titanium and insulated to withstand a crash impact many times to the force of gravity. So because as we imagine, suppose if the aircraft fall to the ground, so with such a high altitude and high pressure, so no matter what, the unit has to withstand that impact. So I believe like the temperature will be around 1000 degrees C for up to 30 minutes, and the immense pressure of lying on the seabed. So usually, like we have seen the scenario, always will have flight crash in the mid of the ocean or in the mid of the ocean. Suppose if it happens, then the wreckages. So it's very highly impossible for us to locate the flight data recorder. So yeah, the FDR will have ELT, emergency lighting transmitter. So it will have a ELT. So the functionality of the ELT is it will transmit. Okay, it will transmit and it will provide the location of the unit. So at least so it will have the lifespan of 30 days. So it has the inbuilt lithium ion battery. So I believe it will have only 30 days of power. After 30 days, so we lose the box. So then it's very highly difficult for us to search the um, black black box. So black box record after flight crash. So right side pictures shows okay. So this is the real picture. I believe like which I have taken from the 777 crash. So this device is engineered to withstand extreme heat, violent crashes, and tons of pressure. So I do believe like all other parts will be gone, but except this FDR should be, no matter, it should be retained actually for further investigation. So I am so I have concluded all so far. Just I gave the overview of avionics, advanced avionics, then flight control system, and bit of electrical system, and just I have concluded with FDR flight data recorder means black box. So I'm concluding as we know that all aircraft have a requirement for essential system such as the engine, propeller, indication. As I say, the subsystems, we have so many subsystems. Each has to play its own role, and again it has to integrate with other subsystems, and finally it has to play a role of a one single system. So and also some system, understanding the aircraft system of the aircraft being flown is critical to its safe operation. So our ultimate aim is we should have to achieve the safe operation for entire flight duration. So this is the ultimate goal in the aerospace aircraft domain. So mm, so so all the references I have taken during in the preparation of the presentation. Any
Thank you.
question?
Thank you, Rob. Questions are there. Hello. Yeah,
Yes.
questions are there. One questions. If there is sudden reduced altitude of aircraft during emergency, produced power is gradually reducing by RAT and potentially risk of overloading the RAM, air turbine, and stored emergency supply like batteries. How such condition is tackled?
Yeah, so battery. So first, so initially, like our first source is generators. So suppose so then the second source will be the battery backup. I believe we have lithium ion battery, which has the capacity of to power the critical subsystems of the aircraft at least for 30 minutes actually. So the pilot will have at least 30 minutes to go for a safe landing. So what I mean to say is, as I mentioned, we have a bus power controller. So that unit will decide, okay, so right now the aircraft is in a emergency mode. So we have to take out the sum of the loads. So only we have to have a critical units, and all, like take for example entertainment systems, those are will be turned off actually, because no need. So those are not considered as a critical units. So then so the at least we'll have 25 minutes of power. Then the 25 minutes is enough to relocate to the safest place, and we can get on. Otherwise we have other as we mentioned, ram air turbine. So the conditions for that, in order to in order to have rat. So the conditions are, the aircraft at least it should be like at least it should be at 125 3000 altitude and 125 knots, and both the left and right generator should be off, means malfunction small function. Then automatically the ram air turbine will deploy, and it will have 12 it will have a capacity of 12 kVA. So then I do believe, like with the 12 kVA, so again as I mentioned, so the bus power control unit will decide to have a critical load on the aircraft, and based on the load analysis principle, then we'll have enough time to go for a safe landing.
Okay, Rao. One more question. Is flight controlling of drones is there?
Flight controlling of drones. uh, I'm not aware of drones, so maybe yeah.
Okay. If you okay,
Yeah,
then it is. Okay, one more question. How feasible is in flight tracking for current aircraft currently in industry? Flight tracking.
flight tracking. Yeah,
Yeah.
yeah. Flight tracking. Yeah, it is one of the tedious component, especially flight tracking. As we know that lot of we have a lot of dedicated air path and a lot of aircrafts will be in the flight phase. Okay, so it's a very so right now we have a plan. So what we are doing, we are planning to track the real aircraft data through the satellite communication. So one of the thing is through the iridium satellite, iridium. So iridium comes under LEO, low earth orbit. So I do believe like we'll have upload and download link of 355 kbps actually. So through 355 kbs and having with the private agency, we can track the path of real time of aircraft.
Okay.
Bangalore, in Bangalore, recently they have introduced instrument landing system, some category.
Mhm.
Can you tell me how pilot will land with controller or with seeing meter? Even poor visibility is there, they will land maybe 50 meters.
Yes, sir. Actually, like HCL company has developed like zero visibility landing system actually. So they have developed the system. So we will have zero visibility landing system in the aircraft. So as I mentioned, like we have advanced avionics. So entire autopilot or the controlling will be taken care by the advanced avionics. So once the zero visibility landing system will decide, okay, do we have what is the level of visibility? So based on that input, so it will take a proper action and we'll have a safe landing.
Okay, Rao, one more question. Is fuel cells being used?
Sorry,
Is fuel cells being used? Fuel cells.
fuel
Hello.
cells. Okay.
Used in flights?
Fuel cells means like I didn't understand what is that fuel in terms of
Using
battery cells.
hydrogen fuel cell battery. I
Okay.
don't think they won't use in aircraft.
Okay. Then
Yeah.
next question.
Yeah. We are using
The ability.
lithium ion batteries, sir. So we have two dedicated lithium ion batteries, nickel cadmium and lithium ion batteries. So which both has the capacity of 32 volt DC. Then I do believe like it will power at least 25 minutes. 25 minutes. It has the life. It has the life of 25 minutes.
Okay, one more questions. The ability to track aircraft in flights has often been overlooked due to the cost implication, but how possible is it?
So yeah, right. Nowadays we have like a digital communication. Okay. So as I mentioned, like tracker and navigation system. So entirely we will communicate with the satellites. So with the advancement of satcom devices which has been fitted in the aircraft, so we definitely we can achieve this without any issues.
Okay. How
Yeah.
temperature sensors are made for high temperature measurement in aircraft?
So as you see, like I showed the picture where we have ADSB probes, so air data probes. So we have dedicated air data probe systems. So four air data probe systems have been fitted in the nose, in the tip of the nose. Actually, we have like totally it is divided as ADSB probe A, B, C, D, C, D. Totally four probes. So that is a sensor, a highly robust sensor. It will sense the altitude and airspeed and outside atmospheric temperature. So we'll have so the aircraft will receive the what sensing elements from the four sensors actually. So I mean to say we have four levels of redundancies. So
Okay.
those sensors will be fed directly to the computational computers. So which is in the forward avionics bay. Then it will process and amplify, and again it will provide the input to the flight crews.
Okay. Next question. Can you name few sensors used in temperature? and altitude sensing. Already you answered. Okay, that
Yeah,
is the answer.
TAT is a one sensor. ADSP is this one sensor. I believe we have heard about Collins Aerospace and Collins Aerospace. Then Saffron Engineering. So they are the manufacturers of highly sensible sensors.
Okay. Then, sir, mathematical modeling is applicable in this electrical system architecture and avionics.
Yes, sir. So currently, I was in US. I was in US in Rockford, for some worked for Collins Aerospace. So they used to manufacture electrical system. Hardly we used to follow suppose DO 178B. Hello.
Sir, Velu Murugan, sir. Okay, continue, sir. Continue, sir. Continue.
Yes, sir. So hardly as I mentioned, we have regulatory agencies, sir. 178B or C. Okay, DO 178B till up to 2012. Later on, they have revised the BC. So for DO 178C for C after 2012. That is for the software component. Yes. So where they have included the modeling based techniques, because with the advancement of computers and electronics and computers, so they have introduced, okay, it's possible, so we can have model based development design methodologies will be applicable in the aerospace industry, so where we can go for certification. Yes, sir. So we have done, sir. So we have done where we can develop, so during our initial phase we'll have model based design. Then as we know that it's very useful during the preliminary design, and we can see, okay, what are the flaws and what are the constraints and what are the limitations. So before the end product comes, actually, so those are the very important for us. So based on that, we will model, and again, as we know that it will generate the auto code also, like at least 80% of the code will be generated and 20% we will do hard coding. So in terms of evaluation, it will be very easy for us.
Okay, sir. One last question. What is the purpose of starter generator? What will be its capacity?
Starter generator, sir. So yeah, because okay, sir, in especially on 787 aircraft, we have starter generator. Okay, so that is called variable VFSG. We will call variable frequency starter generator. So we have generator, it is integrated with the generator. But on the A320 A220 program, that is called C6 aircraft, so we do not have starter generator. We have VFG, variable frequency generator. Okay, so as we know that in order to crank the engine, at least we need at least 100 at least 800 amperes, sir. So when you start the engines, so we can see it will bump till up, it needs 800 amperes to crank the engine. So for that we need a starter generator.
Sir, is there any specific reason to use 787?
Where in the air in the slides?
Yeah, 787 you used.
Yes, sir. Actually, I worked on 787 aircraft. And
is there any specific reason to use 787, sir? Number, it is specific reason is there?
No, sir. So usually that is up to the Airbus or Boeing to have some configuration. Take for example, we have 787, 77, 737. So they will follow their own tradition, and whereas Airbus, they will follow A320, A350, A380. So it's a 787, it's an indication of variant, sir. So 787 means, okay, it has the seating capacity of 250 to 300. So that is their intention, but I'm not aware. Okay, so as we know that we are not the decider. So they will decide, okay, what exactly the configuration name they want.
Okay, sir. Thank you.
Sir, recently while approaching New York, Air India 777 has problem with battery. Without battery, maybe he has landed. About that incident, sir?
No, sir. No, because
Okay.
we will get some snacks. Okay, so when in 2013 I was supporting Boeing, where I heard there was an issue with regards to the battery. So we have some incident, and all the flights were grounded actually for at least 3 months. So that time I was also part of the team for what system integration purpose. But this aware I am not aware, sir. So
This
this.
has happened about 1 year back, maybe. He
Uh-huh.
has landed manually, I think.
Okay, sir. Okay.
Complete battery supply is 0. That's why he has landed maybe manually, I think.
Okay, sir.
News has come. Okay, leave it.
Okay. Thank
Because of some confidential from the Airbus, Rao unable to explain some of the confidential answers because it's the confidential to the company. That's why he taken all the slides from the Google.
That's correct, sir.
That's correct.
Yes, sir.
Okay,
Yes.
I think you answered all the questions. Now,
Sir,
before going to the Mahesh,
sir, one more question is there in the chat box. Why not we fix ejection arrangements of passenger seats while crash landing period, sir?
Sorry, sir. I didn't hear properly.
Why not we fix ejection arrangements of passenger seats while crash landing period, sir?
Crash landing period. Okay. No, sir. I'm not aware. So, as we know that aircraft is a huge complex system. So just I'm part of one subsystem. So maybe the structures guys. So again, involvement of structures. So they will know what are the structural impacts. So if the seat is in which position, inclined position or that position. I'm not aware of structural impact.
thank you for questioning all this. Before going to the vote of thanks by our beloved chairman, I would say some words. When I approached Ram Rao for this FTP talk, first of all, he agreed, but later the problem come to the timing because now he's there around night 2 o'clock. Yes, Rao?
Yes, sir. 2 o'clock.
Yes, nice 2 o'clock. Then we discussed for 1 or 2 days. Then you come to one decision. Then again, Rao agreed. He told that one again there is a problem because today now is a Thursday night, na, for you.
Yes, sir. Thursday night.
It's Thursday night, and you are in Friday. That is the one of the confusion for us. How to keep the session.
Okay.
Then after long discussion, Rao reminded so many times himself. I reminded many times. Finally, Rao is given a very good lecture, very good insight of the aircraft. What you are told that one, the pilot doing in the aircraft, every day I'm doing from the past 5 days. I'm checking the malfunctions function because I'm having the headphone and other things. I'm checking participants feedback and all the participants, what are they doing. Thanks. Now I welcome our beloved chairperson, Professor BP Arisal, to give vote of thanks to Mr. Rao. Sir? BP Aris, sir? Hello?
Good morning, all of you. Am I audible?
It's audible. You can continue.
Yeah. Good morning, all of you. Thank you very much, Mr. Ramarao.
Thank you, sir.
Have really taken us through a wonderful, fascinating walkthrough electrical systems, craft, all the associated challenges. And you also missed black box. All of us have heard about the black box and the of CV. Have unveiled this black box for us. It's no longer black box, has become the true color, that is the orange box for all our participants henceforth. All the electrical systems as systems architecture, their implementation in very lucidly explain all our participants. Very thankful to you, sir. It's very special thanks to you because your talk from Montreal, Canada at this hour is 2 a.m. local time. Is a manifestation.
Hello,
that
sir. Audio missing, sir.
Hello.
Audio, please raise the volume, sir. Be very, sir.
Yeah.
Okay, now come.
This is the maximum what I have. Okay. Yeah. So that you are talking to us at such an odd hour from Montreal is a manifestation of two aspects. One, the technical aspect that technology has enabled us possible, has made this possible. The second one, and most important, is your commitment to our country, your commitment to this, our teachers, so that your experience and expertise reach all our teachers and in turn students. It really enables achieving the goals set out by ATAL government. Very much, sir, to sir, for time, but your special effort of 2 o'clock is normally time to sleep. Very difficult away. That's a human try. Still, in spite of all these shortcomings, you have shown your commitment. Half of the department, all our participants. Once again,
Thank
hope to hear any such talks. Just in case you please make sure that very happy to host you.
Oh, sir, audio is there, but volume is very low, sir.
So this is the maximum that I could. Anyway, I'm done with my vote of thanks. Thank you very much, Mr. Ramarao. Thank you all.
Thank you, sir. Thank you, sir. Thanks a lot, sir.
Ramarao,
Yes,
Mr.
sir.
Ramarao, thanks for your valuable time. Even though very busy schedule, you are agreed to give talk on flight control and taken us to in-depth of the flight, especially electrical wiring and sensors. So we hope same association with us will continue for the future events. Thanks once again. Thanks once again. Okay, thank you.
Thank you, sir. Thanks a lot. Thanks.
Thanks a
And
lot.
have a nice day to all. Thank you.
Thank you. I'll contact you later. Thank you,
Okay,
sir.
sir.
Actually, already this is night. You can take a rest now. Again, tomorrow morning you have to start work.
Okay. Okay,
From
sir.
good night from all of us. Thank you.
Okay, sir. Thank you. Bye.
Thank you. Thank you. Thank you. Maheshan,
Yes, sir.
you can end the meeting.
Yeah.
Again, they have to rejoin by
Join by
11:55. 11:55.
yeah.
Okay, thank you.
Participants, please join by 11:55.
After flying the flight, the morning problem is overcome.
Welcome. Yeah.